In this video, we will introduce Venn diagrams, which is an important tool in understanding sets and their relationships in a more visual way. To illustrate, let's consider the universal set U containing the numbers 1 to 6. If you haven't learned the concept of the universal set before, please watch my previous video on introduction to sets. Suppose we have sets A and B containing these elements. To describe the relationship between the sets U, A, and B, we first draw a large rectangle representing the universal set U. This gives a boundary on the sets and elements, so we just have to focus on drawing sets and elements inside. Let's draw a circle to represent the set A. Before we draw another circle for the set B, we note that there is an element, namely 2, which appears in both set A and set B. So we want to make sure that there is an overlapping region for the two circles, and we write 2 inside that region. Now, we need to write the remaining elements of U in the appropriate regions. 1 and 3 belong to A, so we write them in the circle of A, outside the overlapping region. Similarly for 5 and 6 in B. Lastly, 4 does not belong to A or B, so we just have to write it somewhere outside the circles, but within the rectangle. Note that the shapes representing the sets U, A, and B do not matter. Using a rectangle and circles is just for clarity and consistency. Let's consider more examples. With the same universal set U, suppose we have sets A, B, and C with these elements. In practice, we should always look for any element which appears in more than one set, because it will affect the relative positions of the circles. We see that 4 and 6, namely the elements of B, both lie in A. This means that the circle representing B should lie entirely inside the circle representing A. So they would look something like this. Next, we have the set C, which contains only 1, so we draw it as a circle isolated from A and B. Don't forget to write 2 and 3 somewhere outside the circles, as they don't belong to any of the sets A, B, and C. One more example. Consider the universal set containing A, B, C, D, E, and F, the sets A, B, and C with these elements. We observe that A is in all 3 sets, and B is in sets A and B. So we want to draw the 3 circles like this, where there is an overlapping region for all 3 circles. The element A should lie there. We should also put B in the overlapping region of the circles representing A and B, but outside the region containing the element A. Then, we fill in the remaining elements in the sets, namely C in A, D in B, and E in C. Finally, the element F, which does not lie in any of the sets A, B, and C, should lie somewhere outside the 3 circles. Having seen the Venn diagrams, it is natural for us to introduce set operations. Suppose we have a set A in the universal set U. We define the complement of A, which is denoted by A subscript C, to be the set of elements which are not in A. Observe that this definition is only meaningful if the universal set U is made clear. Let's consider an example. If U is the set of numbers from 1 to 8, and A is a set 2, 4, and 7, then A complement is the rest of the elements in U, namely 1, 3, 5, 6, and 8. In a Venn diagram, the complement of A is simply the region inside the rectangle, but outside the circle. The next set operation is the intersection of 2 sets. The intersection of A and B is the set of elements that are in both A and B. To illustrate, again take the universal set 1 to 8, and suppose A contains 2, 4, 6, 8, and B contains 3, 4, and 6. Then the intersection is just the elements that are common to both A and B, namely 4 and 6. In the Venn diagram, A intersect B is the overlapping region of the 2 circles representing A and B. Now we introduce the union of A and B, which is the set of elements that are in A or B. Note that this "or" is inclusive, which means that the element can be in both A and B. With the previous example, the union is formed by combining the elements of A and B, where any repetition of elements is ignored. The Venn diagram of A union B is the combined region of the two circles representing A and B. The last set operation that I'm going to introduce is the difference between two sets. The difference of B from A, denoted by A\B, is the set of elements that are in A but not in B. Again, using the same example, A minus B is just 2 and 8. The Venn diagram is the region of A taking away the overlapping region of A and B. It is useful to note that A minus B is the same as the intersection between A and the complement of B. Now, let's talk about some useful properties of these set operations. The first one is rather easy and intuitive, and it just says that the complement of A is just A itself. This should not be too confusing, because the only way to be not in a things which are not in A is to be in it. This is just the normal two negatives give a positive notion. Next, we have the so-called commutativity, which states that A union B is the same as B union A, and A intersect B is the same as B intersect A. This is true directly from the definition because we did not impose order when we define the union and the intersection. Similarly, we have associativity, which just means that when we have three sets, it does not matter in which order that we take the union or the intersection, as long as the operations are either both unions or both intersections. In the case that we have a union and an intersection, we have distributivity. If we intersect A with the union of B and C, then it is the same as taking the intersection of A and B first, and then union that with the intersection of A and C. This can be more easily remembered by comparing it with the distributive law in arithmetic, which says that A times bracket B plus C is the same as A times B plus A times C. Similarly, we have A union, the intersection of B and C, equals the union of A and B intersects the union of A and C. Finally, we have the De Morgan's laws, which is arguably the most important property of sets. It is used all the time in various proofs. It states that the complement of A union B is the same as A complement intersect B complement. We can think of it as follows. How can you not be in A or B? Well, you must not be in A, and you must not be in B, and this is exactly what De Morgan's law says. Similarly, we have the complement of A intersect B equals A complement union B complement. Again, in order to be not in both A and B, you must either be not in A or not in B. It will help to use a Venn diagram to help us think about the distributivity and De Morgan's laws, but I will leave them for you to ponder because I will prove them formally in a future video, so stay tuned.